Hello, my friend, and welcome to Orbital Dreams. There is a strange possibility hidden inside motion. A falling object, a swinging pendulum, even a planet moving through space may not be best understood by the forces we can picture. Behind the visible motion, physics found another layer. A stranger rule. A rule where nature's path seems to be shaped by energy, time, symmetry, and something called action. Tonight, we'll follow that hidden rule into Lagrangian mechanics, one of the most elegant and mysterious languages ever used to describe the universe. Chapter 1. The search for a deeper way to describe motion. To understand Lagrangian mechanics is to step into one of the most elegant ideas in all of physics. Motion can be described through a hidden pattern of energy, change, and possible paths, reaching far beneath the visible push and pull of forces. Every day, motion seems simple because we are surrounded by it. A cup falls from a table. A door swings open. A stone rolls down a hill. A planet moves silently around the sun. At first glance, these events look very different from one another. Yet physics asks whether all these motions can be understood through common principles. It asks whether the fall of the cup and the orbit of the planet are separate stories or different expressions of the same underlying language. The first great answer came through Newtonian mechanics. Isaac Newton gave physics a way to connect motion with force. If an object changes its motion, something is responsible for that change. A push, a pull, gravity, tension, friction, pressure, or contact can alter how the object moves. Newton's laws made this idea precise. With this framework, the motion of falling bodies, projectiles, pendulums, tides, and planets could be described with astonishing success. Before Newton, nature often seemed like a collection of separate behaviors. Stones fell because that was thought to be their natural tendency. The moon moved in the heavens according to celestial rules. Earthly motion and heavenly motion were often treated as different kinds of reality. Newton showed that the same basic principles could govern both. The same gravity that pulled objects toward Earth also helped hold the moon in orbit. Motion became something that could be calculated, predicted, and understood. But as physics developed, a quiet difficulty appeared. Newton's method was powerful, but it often required physicists to track every force directly. For simple motion, this works beautifully. If a block slides across a surface, we can think about gravity, normal force, friction, and any applied push. If a ball is thrown through the air, we can describe gravity and perhaps air resistance. But many systems in nature are less direct. A pendulum is forced to move along an arc because a string constrains it. A bead sliding on a curved wire cannot move freely through space. A rigid body rotates while every part of it moves together. A planet may be influenced by several other bodies at once. In such cases, the force approach can become crowded. Some forces are central to the motion, while others mainly enforce constraints. The tension in a pendulum string is real, but it does not usually tell us what we most want to know. It keeps the pendulum bob at a fixed distance from the pivot. It makes sure the bob follows a circular arc. Yet the motion along that arc is governed mainly by gravity and inertia. When everything is described through forces, much of the work may go into handling forces that simply maintain the geometry of the system. This is where the search for a deeper description begins. Physicists gradually discovered that motion could often be understood more naturally by asking a different kind of question. Instead of starting with every force, we can begin with the energies of the system and the ways the system is allowed to move. A pendulum has kinetic energy when it swings and potential energy because of its height in a gravitational field. Its position can be described by an angle rather than by horizontal and vertical coordinates. When we choose the angle as the natural variable, the problem becomes cleaner. We are allowing the system to speak in a language that fits its own motion. This change of perspective is one of the central reasons Lagrangian mechanics became so important. It does not discard Newton's laws. It reaches the same physical conclusions when both methods apply. But it organizes the problem differently. Forces are no longer the first thing we must name. The structure of motion comes forward. The method asks what quantities change, what quantities remain steady, what paths are possible, and how energy is exchanged between motion and position. This does not mean nature is making conscious choices. The language of paths can sometimes sound poetic, as though a particle looks ahead and selects a route. That is not what the theory requires. The deeper idea is mathematical. The actual motion of a system is the one that satisfies a precise condition involving a quantity called action. Action is built from the Lagrangian, and the Lagrangian is usually related to the difference between kinetic energy and potential energy. This condition leads to the same kind of equations of motion that Newton's laws provide, but it arrives there through a broader principle. The beauty of this approach is that it works especially well when motion is constrained, curved, or expressed in unusual coordinates. If a system naturally rotates, we can use angles. If it moves on a sphere, we can choose coordinates that fit the sphere. If several parts move together, we can describe the independent ways the system can change, rather than tracking every individual component in the most awkward possible way. The variables used in Lagrangian mechanics are called generalized coordinates because they do not have to be ordinary distances. They can be angles, lengths, shapes, or any quantities that describe the actual freedom of the system. This idea is surprisingly practical. A pendulum really has only one main way to move if the string length is fixed. It swings by changing its angle. A bead on a wire moves along the wire, even though the wire may curve through ordinary space. A rolling wheel combines translation and rotation, but its motion is tied together by the condition of rolling without slipping. Lagrangian mechanics allows physicists to build these restrictions into the description from the beginning. The unnecessary forces that enforce the restrictions often disappear from the final equation. What remains is the motion that matters. The search for this kind of description did not happen all at once. It grew from the work of mathematicians and physicists who wanted mechanics to become more general, more flexible, and more unified. Newton had given the world a direct and powerful framework. Later thinkers such as Euler and Lagrange developed methods that transformed mechanics into a language of coordinates, energy, and variation. Their work helped reveal that the laws of motion could be written in a form that did not depend on one preferred set of coordinates. That was a profound shift. A law of nature should not become more true or less true just because we describe the same system in a different mathematical language. This point may sound abstract, but it is deeply connected to how modern physics thinks. When a theory remains valid across many coordinate choices, it feels closer to the structure of nature itself. Lagrangian mechanics moves in that direction. It separates what is physically meaningful from what is merely a choice of description. Whether we use distances, angles, or more exotic variables, the underlying motion is the same. The theory gives us a way to find it without being trapped by the first coordinates we happen to choose. There is also something deeply revealing about using energy rather than force as the central language. Forces are local and immediate. They tell us what is pushing or pulling at a particular instant. Energy gives a broader view. It connects position, motion, and transformation. A swinging pendulum repeatedly trades potential energy for kinetic energy and back again. A planet in orbit continually shifts the balance between motion and gravitational potential. A spring stores energy when compressed and releases it into motion. These stories are all different, but energy allows them to be compared through a common structure. Lagrangian mechanics begins with this broader view. It asks us to look beyond the visible motion and notice the invisible accounting beneath it. When an object speeds up, slows down, rises, falls, turns, or oscillates, energy is being redistributed. The Lagrangian captures this redistribution in a compact way. It becomes a kind of summary of the system, a single expression from which the motion can be derived. That is why physicists often speak of writing down the Lagrangian of a system. Once it is known, the behavior of the system is, in a deep sense, encoded. This is one reason the Lagrangian approach became a bridge from classical mechanics to later physics. The same style of thinking appears in electromagnetism, relativity, quantum field theory, and particle physics. Modern theories often begin by asking what Lagrangian describes the fields and particles involved. From that starting point, the equations governing the system can be derived. So although this video begins with familiar motion, the road ahead leads much farther. It leads from pendulums and planets to fields, particles, symmetry, and the architecture of physical law. For now, the important thing is simple. Lagrangian mechanics was born from the desire to describe motion in a deeper and more flexible way. Newton showed how forces produce acceleration. Lagrange helped show how motion can emerge from energy, constraints, and possible paths. These are different windows into the same physical world. One window shows the push and pull of forces. The other shows the quiet structure that makes the motion possible. As we begin this journey, there is no need to rush toward equations. The first step is only to feel the shift in perspective. Motion is no longer just something that happens moment by moment under the command of forces. It becomes part of a larger pattern, shaped by energy and guided by the allowed ways a system can change. The universe still moves as it always has, but we have found a calmer and more spacious way to listen to it. So let the day soften for a while. Let the falling cup, the swinging pendulum, and the distant planet settle into one gentle thought. Beneath all motion, there may be a deeper order, quiet enough to rest in and precise enough to describe the stars. Chapter 2. From Newton's laws to the language of energy. Newton's laws describe motion by following forces, but the deeper story begins when we notice that every motion also carries a changing pattern of energy. Imagine lifting a book from the floor to a table. You feel the weight of it in your hand. You apply an upward force. The book rises. In Newton's language, we can describe the forces acting on the book and explain how they affect its motion. But something else has changed as well. The book now has a different capacity to move if it falls. By lifting it higher, you have stored energy in its position. If it slips from the table, that stored energy will become motion. The fall does not need to be mysterious. The book gains speed because gravitational potential energy is being converted into kinetic energy. This is the language of energy, and it gives physics a wider view of motion. Force tells us how motion changes from instant to instant. Energy tells us how the whole system transforms. The same event can be described in both ways, yet the feeling of the explanation is different. With forces, we focus on pushes, pulls, and accelerations. With energy, we focus on what is stored, what is released, and what changes form as motion unfolds. This shift matters because energy is one of the most reliable concepts in physics. In an isolated system, total energy is conserved. It may move from place to place or change from one form to another, but it does not simply vanish. A moving object carries kinetic energy. An object raised in a gravitational field carries gravitational potential energy. A compressed spring carries elastic potential energy. A warm object contains internal energy linked to the motion and arrangement of its microscopic parts. These forms look very different in daily life, but physics treats them as connected expressions of the same underlying quantity. The idea of kinetic energy is closely tied to motion itself. A slowly rolling ball has less kinetic energy than the same ball rolling quickly. A heavy object moving at the same speed as a lighter one has more kinetic energy. Speed matters strongly because increasing speed increases kinetic energy very rapidly. This is why a small stone dropped from a great height can strike with surprising force, and why a car moving quickly carries much more energy than it seems to when standing still. Motion is not merely a change in position. Motion is a storage of energy in movement. Potential energy is subtler because it often feels invisible. A stretched bowstring, water behind a dam, a raised hammer, and a planet in a gravitational field all contain energy because of arrangement. The energy is not seen as a glow or a substance inside the object. It is present because the system has the ability to change. If the bowstring is released, it can launch an arrow. If the water is allowed to flow downward, it can turn turbines. If the hammer falls, it can do work. Potential energy belongs to the configuration of a system, to the way its parts are placed relative to one another. The word work has a special meaning in mechanics. In everyday speech, work can mean effort, concentration, or time spent on a task. In physics, work is connected to force acting through a distance. When you push a box across the floor, your force can transfer energy to the box or to the surface through friction. When gravity pulls an object downward, gravity does work as the object falls. This connection between force, distance, and energy is one of the bridges from Newton's laws to energy methods. The motion still obeys Newton's laws, but we can often understand the result by tracking energy changes instead of solving every detail of the force at every instant. A simple swing shows the idea beautifully. At the highest point of its arc, the swing momentarily slows. Much of its mechanical energy is stored as gravitational potential energy because the seat and rider are lifted higher. As the swing descends, this potential energy becomes kinetic energy. At the lowest point, the swing moves fastest. Then it rises on the other side, and kinetic energy is transformed back into potential energy. If there were no friction and no air resistance, this exchange would continue with perfect regularity. In the real world, some mechanical energy gradually becomes internal energy in the air, the chains, and the supports, so the swing slows unless energy is added again. This example also shows why energy can simplify our thinking. To know the speed of the swing at the bottom, We may not need to follow every tiny change in force along the entire arc. Under ideal conditions, we can compare the energy at the top with the energy at the bottom. It gives a view of the entire motion, rather than a frame-by-frame account. This is especially useful in systems where the forces are complicated, but the energy is easier to write down. A ball rolling inside a smooth bowl experiences changing contact forces from the bowl. The direction of the normal force changes constantly, and those details can make the direct force approach feel awkward. But the ball's height and speed are easier to understand. As it climbs, it slows. As it descends, it speeds up. The bowl shapes the allowed path, while gravity and motion trade energy back and forth. Energy lets us see the central story. The language of energy also introduces a more abstract but powerful way of describing physical systems. Instead of asking only where an object is and what force acts on it, we can ask what energy belongs to each possible arrangement. This gives us an energy landscape. A marble in a bowl tends to move toward the lower region because lower gravitational potential energy is available there. A stretched spring tends to return toward its relaxed length because that arrangement has lower elastic potential energy. A system does not need awareness to behave this way. The motion follows physical laws, and those laws can be expressed through how energy changes across possible configurations. In Lagrangian mechanics, this energy viewpoint becomes central. The Lagrangian is built from the relationship between kinetic energy and potential energy. We do not need to write the mathematical expression here to understand the idea. Kinetic energy represents motion. Potential energy represents arrangement and stored possibility. The Lagrangian combines these ingredients in a way that allows the equations of motion to emerge. It captures what the system is doing and what the system could do based on its freedoms and constraints. This is why the transition from Newton's laws to energy is more than a change in calculation style. It changes what we notice. A force-based description may begin with a diagram of arrows. An energy-based description begins with the system as a whole. What can move? How is energy stored? How is energy exchanged? Which arrangements are possible? Which quantities stay constant? These questions are calmer, but they are also very deep. They prepare the mind for the principle of action, where the path of motion is found through a global condition rather than through local force alone. Still, energy methods work within clear physical limits. If friction, air resistance, or other dissipative effects are important, mechanical energy may decrease because some of it becomes internal energy, sound, or other forms. Total energy remains conserved when the broader environment is included, but the energy of the simple mechanical motion may fade. A pendulum slows because energy is transferred into the surrounding world. A sliding block stops because organized motion becomes microscopic agitation in the block and surface. Energy is conserved, but it may become less useful for producing large-scale motion. This point keeps the idea grounded. When physicists speak of energy conservation, they are not saying that every visible motion continues forever. They are saying that energy changes form according to precise rules. The motion of a bicycle slows when brakes are applied because kinetic energy becomes thermal energy in the brake pads, wheels, and air. The energy has not disappeared. It has spread into forms that are harder to reverse. This is one of the reasons energy language eventually connects mechanics with thermodynamics, heat, and the direction of time. In the context of Lagrangian mechanics, however, We begin with systems where kinetic and potential energy give a clean description. These ideal systems are not childish simplifications. They are starting points that reveal structure. A frictionless pendulum, a smooth orbit, a mass on a spring, or a bead moving along a wire can teach us principles that later survive in more advanced theories. By studying clean cases first, physics finds patterns that would be hidden inside the noise of every real-world detail. The power of energy is that it belongs to the whole motion. It lets us compare different moments without losing the unity of the system. It shows how motion can be understood as transformation rather than as a sequence of disconnected changes. A falling object, a swinging pendulum, and an orbiting planet are all engaged in exchanges between movement and stored possibility. Once we begin to see that, the path toward Lagrangian mechanics becomes natural. Newton's laws remain one of the great achievements of human thought. They tell us how motion responds to force with extraordinary precision. But the language of energy lets us step back and see motion as part of a larger balance. It reveals that beneath acceleration and force, there is a quieter accounting, a conservation that runs through the changing world. As this chapter settles, you can imagine every motion around you softening into that balance. The earth turning, the air shifting, the body breathing, the distant planets moving through space. Everywhere, energy changes form patiently and silently. And for now, you do not need to chase every force. You can simply rest with the idea that motion has a deeper rhythm and that physics is slowly teaching us how to hear it. Chapter 3. What the Lagrangian really is. The Lagrangian is one of those rare ideas in physics that looks almost modest at first, yet quietly contains the motion of an entire system. When people first hear the word Lagrangian, it can sound like something distant and technical, as though it belongs only on a blackboard filled with symbols. But the basic idea can be approached gently. A Lagrangian is a mathematical description of a physical system built so that the laws of motion can be drawn from it. It is a compact way of saying what kind of motion the system has, what kind of stored energy it carries, and what freedoms are available to it. In many ordinary mechanical systems, the Lagrangian is based on a simple relationship between kinetic energy and potential energy. Kinetic energy belongs to motion. Potential energy belongs to arrangement, position, or stored possibility. The Lagrangian compares these two parts in a very specific way. It does not simply add up all the energy in the system. It measures the balance between motion and stored configuration. And that balance turns out to be exactly the kind of information needed to describe how the system changes. This can feel strange at first because total energy sounds more natural. If energy is conserved, why not build mechanics only from total energy? The answer is that total energy tells us something important about what remains constant, but it does not always directly tell us how the system moves from one instant to the next. The Lagrangian is designed for motion. It is sensitive to position, speed, and the allowed ways the system can change. It carries the information needed to produce the equations of motion, even when those equations would be awkward to find by listing forces one by one. Think of a pendulum. To describe it with ordinary coordinates, we could track the horizontal and vertical position of the bob as it swings. But the bob is held by a string, so it cannot move freely in every direction. Its distance from the pivot stays fixed. The natural description is the angle of the string. The Lagrangian can be written in terms of that angle, and how quickly the angle changes. This means the description follows the true freedom of the system instead of forcing us to use coordinates that carry unnecessary clutter. The Lagrangian is therefore more than a quantity with the units of energy. It is a carefully chosen expression that fits the system. It depends on the variables that describe the system's configuration and on how those variables are changing. In some cases, it may also depend directly on time. If a support point is moving, if an external field changes, or if some condition is being driven from outside, time itself can appear in the description. The Lagrangian is flexible enough to handle these possibilities while keeping the same basic logic. A useful way to imagine it is as a compressed instruction for the system. It binds place, motion, and physical arrangement into a single mathematical statement. It says how movement and configuration relate for this particular situation. Once that expression is known, a standard procedure can unfold from it. The system's actual motion is then found through the principle of action, which we will explore more fully in the next chapter. This is what makes the Lagrangian feel so powerful. Instead of beginning with every force, every contact, and every internal restriction, we begin with the energies and the true degrees of freedom. The degrees of freedom are the independent ways the system can move. A free particle in space has several independent ways to change its position. A pendulum with a fixed string has only one main independent motion, its angle. A double pendulum has more than one angle, and its behavior becomes much richer. In each case, the Lagrangian is built from the ingredients that actually describe the system. The idea of degrees of freedom is important because it removes confusion. Real objects are surrounded by constraints. A train is constrained by rails. A bead may be constrained by a wire. A door is constrained by hinges. A planet is shaped by gravity and initial conditions. Lagrangian mechanics allows us to choose variables that respect these situations from the start. When the description matches the freedom of motion, the mathematics becomes more natural. There is a subtle point here. The Lagrangian itself is not usually something we measure directly with an instrument. We can measure positions, speeds, times, masses, and energies. The Lagrangian is a constructed object made from measurable ingredients whose value lies in what it allows us to derive. It is less like a single reading on a dial and more like a sentence written in the language of mechanics. If the sentence is written correctly, the motion follows from it. Many of the most useful ideas in physics have this kind of abstract precision. A field is described through values spread through space and time. Entropy describes the organization and number of microscopic possibilities. A wave function describes probabilities in quantum theory. The Lagrangian belongs to this family of ideas. It is abstract, but it is not vague. Its abstraction gives it reach. Consider a mass attached to a spring. When the mass moves, it has kinetic energy. When the spring is stretched or compressed, it has potential energy. The Lagrangian captures the relationship between these two states. From it, one can obtain the familiar oscillating motion. The mass moves toward equilibrium, passes through it, slows, reverses, and repeats. The Lagrangian does not need to narrate this motion step by step. It encodes the structure from which the motion arises. The same kind of thinking applies to a planet moving around a star. The planet has kinetic energy because it is moving through space. It has gravitational potential energy because of its position relative to the star. A Lagrangian for this system captures the balance between orbital motion and gravitational attraction. From that balance, the curved path of the orbit can be derived. The description is compact, yet it contains the long sweep of the planet's journey. This compactness becomes even more valuable as systems become complicated. A machine with several moving parts, a molecule with vibrating atoms, a field spread through space, or a particle moving under constraints can all be described with Lagrangian ideas. The form of the Lagrangian may become more advanced, but the guiding thought remains recognizable. Find the variables that describe the system. Describe how motion contributes. Describe how interactions and configurations contribute. Put these pieces into the Lagrangian, then let the variational principle reveal the motion. The word variational simply means that we consider possible changes. In Lagrangian mechanics, the actual path of a system is compared with nearby possible paths. The correct path is the one for which the action has a special stationary property. This does not mean the path is always the shortest or easiest in the everyday sense. The word stationary has a precise mathematical meaning. It means that very small changes to the path do not change the action in the first-order way one might expect. The details can wait, but the intuition is worth holding. The Lagrangian helps decide which possible motion becomes the real one. This is where the idea begins to feel different from the everyday picture of cause and effect. In Newtonian thinking, we often imagine forces acting at each instant, pushing the object into the next moment. In Lagrangian thinking, the whole path becomes part of the description. The system's motion is connected across time by the action. Both views agree when applied correctly, but they give different mental pictures. The Lagrangian view feels less like a sequence of commands and more like a pattern that the full motion satisfies. This pattern-based view explains why the Lagrangian became so central beyond simple mechanics. In modern physics, one often begins by proposing a Lagrangian that respects certain symmetries. If the theory should behave the same in every location, this shapes the allowed form. If the theory should behave the same in every direction, this adds another condition. If the theory must respect relativity or quantum principles, the Lagrangian must be built accordingly. From this single central object, the behavior of fields and particles can be derived. That may sound far away from a pendulum, but the connection is real. The same kind of object that describes a swinging mass can also be generalized to describe fields filling space. In field theory, the Lagrangian is assigned to quantities defined at every point in space and time. The mathematics becomes deeper, yet the spirit is familiar. Nature is described through a compact expression, and the motion or evolution of the system comes from it. The Lagrangian also reveals something about the style of physics itself. Physics is a search for descriptions that are simple enough to use and deep enough to survive many different situations. The Lagrangian succeeds because it is both practical and revealing. It helps solve problems, and it also hints at why laws of nature have the form they do. So, what is the Lagrangian really? It is the energy-shaped heart of a system's motion. It is a compact description built from motion, configuration, and freedom. It is a bridge between the concrete world of moving objects and the deeper principle of action. It tells physics how to listen to a system in the language the system itself seems to prefer. And as this idea settles, there is no need to force it into sharp edges all at once. Let it remain simple for now, Every moving system carries a hidden structure, and the Lagrangian is one quiet way of writing that structure down. The day can loosen a little around that thought, as if motion itself has become softer, slower, and easier to understand. Chapter 4. The Principle of Least Action. The principle of least action is one of the deepest ideas in physics, because it suggests that motion is not only pushed forward moment by moment, but also shaped by a hidden rule connecting an entire path through time. At first, the idea can sound almost impossible. We are used to thinking of motion locally. A ball is here, then it is there. A planet moves slightly along its orbit, then slightly farther. A pendulum swings through one instant, then the next. In ordinary thought, the present leads into the future through a chain of causes. The principle of least action keeps that picture, but it also adds another layer. It says that the complete path taken by a physical system has a special property when compared with nearby possible paths. This does not mean an object knows where it is going. A falling stone does not examine future routes before choosing one. A planet does not plan its orbit. Physics is not giving matter a mind. The principle is mathematical. It says that when we calculate a quantity called action for the actual motion of a system and compare it with the action for slightly different imagined motions, the actual motion is the one where the action is stationary. The word least is therefore a little misleading if it is taken too literally. In many familiar cases, the actual path does make the action smaller than nearby alternatives, at least over a suitable interval. But the deeper principle is called stationary action, because the action may sometimes be a minimum, a maximum, or a more subtle saddle-like value. The important point is that tiny changes to the real path do not create a tiny first-level change in the action. The path sits at a special balance point among the possible paths. To understand action gently, imagine watching the motion of a system from a beginning moment to an ending moment. At each instant, the system has a Lagrangian, which reflects the relationship between motion and stored configuration. Action is what we get when we accumulate the Lagrangian along the whole path through time. It is not just a snapshot. It is a record of the entire journey, gathered continuously from beginning to end. This makes action different from ordinary energy. Energy describes the state of a system at a given moment, and in many cases, the total energy remains constant. Action belongs to the path. It depends on how the system moves between moments. Two imagined paths may begin and end in the same places, yet have different actions because the motion between those endpoints is different. One path may move quickly early and slowly later. Another may move smoothly. Another may wander away and return. The principle says the real path is the one that gives the action its stationary character. A simple way to feel the idea is to think about a ball thrown through the air, leaving one point and arriving at another. Many imagined paths could connect those points. The ball could rise too high, curve too low, or follow a strange shape that no real thrown ball would take. Newtonian mechanics would say that gravity determines the ball's acceleration at every instant. Lagrangian mechanics says something equivalent in a different voice. Among the possible nearby paths connecting the same endpoints in the same time, the real path is the one for which the action is stationary. These are not competing truths. They are two ways of expressing the same physical law for systems where both methods apply. Newton's laws speak in the language of forces and acceleration. The action principle speaks in the language of entire paths. This second language can feel less familiar, but it often reveals patterns that the force picture hides. One of the most remarkable features of the action principle is its unity. The same idea can describe a falling object, a pendulum, a vibrating spring, a planet in orbit, a ray of light moving through changing materials, and later, with more advanced mathematics, fields spread across space and time. In each case, the physical system follows a rule that can be expressed through a quantity accumulated along its possible history. The details change from system to system, but the structure remains recognizable. The word possible is important here. In mechanics, we do not compare the real path with every fantasy imaginable. We compare it with nearby paths that respect the basic conditions of the problem. The starting and ending moments are fixed. The starting and ending configurations are usually fixed for the comparison. The paths are allowed to vary in between. These imagined variations are mathematical tools. They let us test which path has the stationary action property. This way of thinking may seem strange because it looks at motion as a whole. Instead of asking only what happens at this instant, it asks which complete history fits the principle. Yet when the mathematics is carried through, the result becomes local again. The principle of stationary action leads to equations that describe how the system changes at each moment. This is one of its quiet wonders. A global condition on the path produces the ordinary moment-by-moment laws of motion. There is a beautiful example from optics that helps make the idea feel less alien. Light passing from air into water bends. In one description, this bending happens because light travels at different speeds in different media, and the wavefront changes direction at the boundary. Another older principle says that the path taken by light makes the travel time stationary. This is often called the principle of least time, though the same warning applies. Stationary is the safer word. The ray bends in just the way required for this special condition. Mechanics and optics are not the same theory, but the resemblance is powerful. Nature often seems describable by stationary principles. The action principle became especially important because it is independent of our choice of coordinates. If we describe a system with angles, distances, curved coordinates, or other suitable variables, the principle keeps its form. This matters because nature does not care which coordinate grid we find convenient. A good physical law should survive a change in description. The action principle does this with unusual grace. It allows us to express motion in the variables that best match the system while preserving the same underlying rule. Consider again a pendulum, but now focus on its whole swing rather than on the forces in the string. The pendulum moves between positions through a path allowed by its fixed length. We can imagine slightly different swings between the same endpoints. Some would spend too much time high up, some would move in unnatural ways, and some would fail to match the balance between motion and gravity. The real swing is special because the action built from its Lagrangian becomes stationary under small allowed variations. Out of that condition comes the familiar swinging motion. The principle does not say that nature avoids effort in the ordinary human sense. It does not say that the universe is lazy. It says something more precise and more interesting. Physical motion is constrained by a mathematical balance between how a system moves and how it is configured. The real path is the path where this balance has the stationary action property. The poetry of the phrase is beautiful. but the science lives in the precision. This precision becomes even more valuable in advanced physics. When physicists study fields, they often begin with an action. The fields may represent electromagnetism, matter, or other physical quantities. The correct evolution of those fields comes from requiring the action to be stationary. The same architecture appears in relativity, where space and time are woven into a single framework. The action principle becomes a common thread running through many levels of physical law. In quantum physics, the relationship becomes especially fascinating. Particles are no longer described in the same simple way as tiny classical objects following one definite path from the beginning. Yet action still matters deeply. In one formulation, many possible paths contribute to the behavior of a quantum system, and paths near stationary action reinforce one another most strongly in the classical limit. This helps explain why ordinary objects appear to follow the classical path predicted by the principle of stationary action. There is another reason the principle feels profound. It suggests that the laws of motion are not merely instructions applied at each point. They can also be seen as conditions on the form of a history. A physical path is not just a line drawn through space. It is a path through the space of possibilities, judged by a quantity that gathers the system's behavior through time. In this view, motion becomes less like a sequence of accidents and more like a coherent pattern. For an average person, the essential idea can be held without technical detail. Take a system. Imagine all the nearby ways it might move between the same beginning and ending conditions. For each possible motion, there is a quantity called action, built from the Lagrangian over time. The real motion is the one where that action is stationary. From this single statement, the equations of mechanics can be derived. The principle of least action is therefore a doorway. It leads from forces to paths, from moments to histories, from visible motion to hidden structure. It does not make the universe mystical, but it does make the universe feel beautifully ordered. It shows that beneath falling, swinging, orbiting, and vibrating, there is a rule of remarkable calm and economy. So let this idea rest softly in the mind. The world does not need to be chased one instant at a time. Its motions can be understood as whole paths, held in a quiet balance. And as the day loosens its grip, you can imagine the universe moving through its possible histories with silent precision, following a principle that is both gentle enough to contemplate and deep enough to guide the stars. Chapter 5. The Euler-Lagrange equation, motion from a single rule. The Euler-Lagrange equation is the point where the quiet beauty of least action becomes a usable law of motion. Until now, the idea of Lagrangian mechanics may have felt broad and almost atmospheric. We have spoken about energy, possible paths, and the action accumulated along the motion through time. Those ideas are powerful, but physics also needs a way to calculate. It needs a rule that can take the Lagrangian of a system and turn it into the actual motion we observe. That rule is the Euler-Lagrange equation. The Euler-Lagrange equation tells us how the Lagrangian must behave when the path of a system is the real physical path. It is the condition that comes out of stationary action. If the action has that special balance property, then the coordinates describing the system must obey a particular relationship. That relationship is the Euler-Lagrange equation. A simple way to understand it is to imagine that the Lagrangian can respond to two kinds of change. It can respond to where the system is, and it can respond to how fast the system is changing. For a pendulum, this means the Lagrangian depends on the angle of the pendulum and on how quickly that angle changes. For a spring, it depends on how far the mass is from its relaxed position and on how quickly the mass is moving. For a planet, it depends on position in space and on the planet's velocity. The Euler-Lagrange equation connects these two responses. It says in words that the way the Lagrangian responds to position must be balanced with the way its response to velocity changes over time. This sentence is the heart of the equation. Position and motion are linked through the Lagrangian, and the correct path is the one where that link satisfies the rule. This may sound abstract, so consider a mass attached to a spring. If the mass is pulled away from the relaxed position, the spring stores potential energy. The farther it is pulled, the stronger the restoring tendency becomes. At the same time, the mass has kinetic energy when it moves. The Lagrangian carries both pieces of information. When the Euler-Lagrange rule is applied, it produces the familiar back and forth motion of the oscillator. The mass accelerates toward the center, passes through, slows as the spring stretches the other way, then returns again. The rule does not need to be told separately that the spring pulls the mass back. That information is already contained in the potential energy. It does not need to be given a frame-by-frame description of the motion. The equation extracts the motion from the structure of the Lagrangian. This is what makes the method feel so elegant. Once the right Lagrangian is written, the motion follows from a single general procedure. The same idea works for a pendulum. The pendulum's angle describes its position. Its changing angle describes its motion. Gravity gives it potential energy depending on its height, and swinging gives it kinetic energy. When these ingredients are placed into the Lagrangian and the Euler-Lagrange rule is applied, the equation of the pendulum appears. The result tells us how the angle changes with time. For small swings, the motion becomes close to simple harmonic motion. For larger swings, the behavior is still governed by the same principle, though the exact motion is more complicated. This is one of the strengths of the Euler-Lagrange equation. It can use an ordinary distance, an angle, or another variable that fits the system. It works with generalized coordinates. These are the natural coordinates chosen to describe the independent ways a system can move. If a bead slides along a curved wire, the coordinate can be distance along the wire. If a door swings on a hinge, the coordinate can be the angle of the door. If a machine has several linked moving parts, each independent motion can have its own coordinate. Newtonian mechanics can describe all these situations too, but it often requires more attention to constraint forces. The Euler-Lagrange method often lets those constraint forces fade into the background when the coordinates are chosen well. The wire, hinge, or rod still matters because it limits the possible motion. Yet the final equation can focus on the real freedom of the system rather than on the forces that merely enforce the constraint. This is why Lagrangian mechanics feels so natural in complicated systems. Imagine a bead sliding without friction on a curved track. The track pushes on the bead to keep it on the curve, and that push changes direction from point to point. If we tried to follow that contact force directly, the calculation could become messy. With the Lagrangian method, we can describe the bead's allowed position along the track, write the kinetic and potential energies in terms of that position, and then apply the Euler-Lagrange equation. The geometry of the track is built into the coordinate. The motion emerges without needing to solve for every detail of the normal force. The equation also has a deeper meaning. It shows that the laws of motion can be derived from a condition on a quantity spread over time. We begin with the action, which belongs to an entire path. We ask for the path where the action is stationary. From that broad condition, the Euler-Lagrange equation appears as a local rule that must hold at each moment. This is a remarkable bridge. A statement about whole histories becomes an equation for moment-by-moment motion. That bridge is one reason the equation is so central in theoretical physics. It gives a way to move from a compact description of a system to its dynamical laws. The Lagrangian is like the seed. The Euler-Lagrange equation is the method that lets the seed unfold into motion. For a simple mechanical system, the result may be the motion of a pendulum or a spring. For a field, the result may be a field equation describing waves, particles, or interactions across space and time. The word equation can make the idea feel narrower than it really is. In practice, there is one such rule for each independent coordinate of the system. A system with one coordinate gives one equation of motion. A system with several independent coordinates gives several linked equations. These equations can influence one another because the coordinates may be connected through the energy of the system. A double pendulum, for example, has more than one moving angle, and each angle affects the other. The Euler-Lagrange method produces the coupled equations that describe their shared motion. This is where complex behavior can arise from simple principles. A double pendulum can behave in ways that are extremely sensitive to its initial state. A rotating body can exchange energy between different kinds of motion. A molecule can vibrate through many connected patterns. The Euler-Lagrange equation does not guarantee that the resulting motion will be easy to predict. It guarantees that the motion follows from a consistent principle. That distinction is important. Physics often gives us the laws governing a system before it gives us an easy solution. Some equations can be solved neatly. Others require approximation, numerical calculation, or careful interpretation. Lagrangian mechanics does not magically make every problem simple. Its power is that it organizes the problem correctly. It gives us a unified path from physical description to dynamical law. The Euler-Lagrange equation also helps reveal conserved quantities, especially when the Lagrangian has symmetry. If a coordinate does not appear directly in the Lagrangian, but the rate of change of that coordinate does, then a related quantity is conserved. This is one of the first signs of the deep connection between symmetry and conservation. Later, this connection becomes one of the most profound results in physics. The Euler-Lagrange framework makes such patterns visible. For example, if the Lagrangian of a system does not change when the whole system is shifted in space, momentum conservation appears. If it does not change as time passes, energy conservation is connected to that time symmetry. If it does not change under rotation, angular momentum conservation appears. These ideas will become clearer later, but the seeds are already present. The equation is more than a tool for finding acceleration. It is a doorway into the hidden order of physical laws. Another beautiful aspect is that the equation does not depend on our personal viewpoint. We may choose coordinates for convenience, but the physical motion does not belong to the coordinates. The Euler-Lagrange method allows different descriptions to lead to the same real behavior. This helps physics separate the law from the language used to express it. When the description is handled correctly, the motion remains the same. This coordinate freedom becomes essential in modern physics. When space, time, fields, and geometry become more involved, the ability to write laws in flexible forms is extremely valuable. A physical theory can begin with an object that summarizes the system, then produce motion through a general rule. This style of thinking reaches far beyond the examples of classical mechanics. Yet the ordinary examples remain the best place to feel the idea. A ball rolling in a bowl, a swing moving through an arc, a spring breathing back and forth, a planet tracing its orbit. Each of these motions can be seen as the outcome of a Lagrangian passing through the Euler-Lagrange rule. The world moves in many shapes, but the method behind those shapes can be shared. So the Euler-Lagrange equation is motion from a single rule. It is the practical voice of stationary action. It takes the Lagrangian, listens to how it depends on position and change, and returns the path the system must follow. It is precise enough for calculation and broad enough to guide modern theories of nature. Let this thought become gentle now. Beneath the movement of things, there may be no need for noise or struggle in the description. A single rule can unfold a pendulum's swing, a planet's curve, and the vibration of matter. The universe moves with complexity, yet its laws can sometimes arrive with surprising quietness. And for this moment, that quietness is enough. Chapter 6. Generalized coordinates. Choosing the right language for nature. Generalized coordinates reveal a quiet secret of physics. Sometimes motion becomes clearer only after we stop describing it in the most obvious way. In everyday life, position usually means location in ordinary space. We think of left and right, up and down, forward and backward. A person walks across a room, a car moves along a road, a stone falls through the air. For many simple situations, this kind of description works perfectly well. We can say where something is, how fast it is moving, and how its motion changes with time. But nature does not always move in ways that fit comfortably into ordinary straight-line coordinates. A door does not wander through a room freely. It turns around its hinge. A wheel does not simply slide forward. It rolls while rotating. A pendulum does not move wherever it likes. Its bob follows an arc because the string keeps it at a fixed distance from the pivot. A bead on a wire may travel through a complicated curve, yet its real freedom is only to slide along that wire. If we describe these systems with ordinary coordinates alone, we may include more information than the motion actually needs. We may track horizontal and vertical positions even though the system is restricted to a curve. We may write down forces whose only role is to keep the object on its allowed path. The description can become heavier than the physical idea. Lagrangian mechanics offers a different approach. It asks us to choose coordinates that match the motion itself. A generalized coordinate is any variable that describes one independent way a system can change. It might be a distance, but it does not have to be. It can be an angle, a length, a position along a curve, a rotation of a rigid body, or another quantity that captures the system's actual freedom. The word generalized means that physics is no longer limited to the familiar coordinate grid. We are free to use the language that makes the system simplest. Take the door as a calm example. To describe every point on the door in ordinary space would be possible, but unnecessary. A well-mounted door has one main freedom. It opens or closes by changing its angle around the hinge. That angle tells us almost everything we need about the door's configuration. The hinge quietly handles the constraint. The generalized coordinate follows the motion that remains. A pendulum has the same kind of lesson. Its bob moves through ordinary space, but the length of the string is fixed. The bob cannot choose its distance from the pivot. Its meaningful motion can be described by the angle of the string from the vertical direction. That single angle becomes the natural coordinate. Instead of forcing the pendulum into a rectangular grid, we let its own geometry guide the description. This is more than convenience. Choosing the right coordinate can reveal the structure of a problem. When the variable matches the system, the energy becomes easier to express. The kinetic energy follows how the coordinate changes with time. The potential energy follows how the configuration changes. The Lagrangian can then be written in a form that speaks directly to the system's real motion. The number of generalized coordinates needed is related to the system's degrees of freedom. A degree of freedom is an independent way the system can move or change. A free particle moving in ordinary space has several independent position choices. A pendulum with a rigid, fixed-length string has fewer. A double pendulum has more because one angle describes the upper arm and another describes the lower arm. A rigid body rotating in space needs variables that describe its orientation. The right set of coordinates depends on what is allowed to change independently. This is where constraints become important. A constraint is a restriction on motion. A string of fixed length, a surface, a hinge, a rail, or a rolling condition can reduce the true freedom of a system. In the force-based approach, constraints often appear through forces of tension, support, or contact. In the Lagrangian approach, many constraints can be absorbed into the choice of coordinates. We describe only the motion that is possible, and the impossible motion never enters the problem in the first place. Imagine a bead sliding on a circular hoop. The bead moves through space, but if it remains on the hoop, its position can be described by an angle around the circle. The hoop's contact force keeps it on the track. If the track is smooth, that contact force does no work along the path of motion. Lagrangian mechanics can often avoid solving for that force directly. The coordinate already knows that the bead belongs on the hoop. The motion along the hoop becomes the focus. This ability becomes even more valuable in curved or rotating systems. A planet's orbit may be easier to describe with a distance from the central body and an angle around it, rather than with separate straight-line coordinates. A rotating disk is naturally described by an angle. A small mass moving on a spherical surface may be described by two angles. The coordinates bend with the problem instead of making the problem bend to the coordinates. There is a quiet philosophical lesson here, but it is a scientific one. The laws of nature should not depend on the human choice of labels. The actual motion of a pendulum is the same whether we describe it with an angle or with positions in a rectangular grid. The bead does not care which symbols we use. The planet does not know our coordinate system. A good physical method should allow different descriptions while preserving the same physical content. Generalized coordinates help make that possible. They separate the physical system from the bookkeeping system. The coordinates are tools chosen for clarity. If a coordinate makes the energy simple, respects the constraints, and captures the true freedom of motion, it is a good coordinate. Another coordinate may also work, but it may make the calculation less graceful. Physics does not demand that we choose the hardest language available. This is especially important in systems with many moving parts. A robot arm, for example, may consist of several connected segments. Each joint has an angle. Describing every point of every segment in ordinary space would create a large and tangled problem. Describing the arm through joint angles is far more natural. The generalized coordinates follow the actual controls of the system. The same idea appears in machines, vehicles, satellites, molecules, and many other systems where motion is organized by connections and restrictions. In molecular physics, atoms can vibrate, rotate, and bend relative to one another. A molecule with several atoms may have many possible motions, but those motions are not best understood by tracking every atom independently in the most basic way. Physicists often look for collective coordinates, such as stretching, bending, or twisting patterns. These coordinates describe how the molecule changes as a whole. The language of generalized coordinates prepares the way for that kind of thinking. The method also helps when a system has symmetry. If a coordinate describes a direction in which the system can change without altering the Lagrangian, that coordinate may reveal a conserved quantity. A coordinate related to rotation can point toward angular momentum. A coordinate related to position can point toward momentum. The coordinate is then more than a convenience. It becomes a clue to a hidden conservation law. This connection will become central later, when symmetry enters the story more fully. For now, it is enough to see that generalized coordinates are a way of listening carefully to the system. Instead of imposing a rigid description from outside, we ask what the system can actually do. Can it rotate? Can it slide along a curve? Can it stretch? Can it swing? Can it change shape? Each independent answer can become part of the coordinate language. This is one reason Lagrangian mechanics feels unusually elegant. It adapts. It does not require all systems to be described as though they were simple particles moving freely in straight lines. It can follow curved paths, constrained motions, and linked components. It gives the physicist permission to choose a description that belongs to the problem. The result is a calmer view of complexity. A system that first looks difficult may become understandable when its real freedoms are named. The door is an angle. The pendulum is an angle. The bead is a position along a path. The rolling wheel is translation tied to rotation. The robot arm is a collection of joint angles. The molecule is a set of coordinated motions. The world remains rich, but the description becomes more honest. And this honesty is the heart of generalized coordinates. They remind us that understanding does not always come from adding more details. Sometimes it comes from choosing the right details. Motion becomes clearer when we describe only the freedoms that matter, in the language the system naturally suggests. So as this chapter comes to rest, imagine the many motions around you becoming simpler in the mind. A door turning softly on its hinge, a pendulum tracing its arc, a planet curving through the dark, each one moving in its own proper language. There is no need to force the world into a harsher shape tonight. Let it move as it moves, and let the right description rise gently to meet it. Chapter 7. Constraints, Symmetry, and the Hidden Simplicity of Motion. Motion often looks complicated because we see every detail at once, but constraints and symmetry can reveal that a system has far fewer true possibilities than it first appears to have. A constraint is a rule that limits how something can move. It may be imposed by a physical object, like a rail, a string, a hinge, or a surface. It may also come from a relationship inside the system, such as the fixed distance between two connected parts. In ordinary life, constraints are everywhere. A train follows tracks, a drawer slides along guides, a wheel rolls on the ground, a satellite remains guided by gravity, a child on a swing moves along an arc rather than drifting freely through space. In mechanics, these restrictions are not minor details, they shape the entire motion. A bead on a wire would move very differently if the wire vanished. A pendulum bob would fall differently if the string broke. A rolling wheel would behave differently if it slipped freely across ice. The constraint does not merely decorate the problem, it defines the space of possible motion. The challenge is that constraints can make a force-based description feel crowded. The forces that maintain a constraint are real, but they may not be the forces we care about most. A table pushes upward on a book, so the book does not fall through it. A hinge pushes on a door, so the door stays attached while rotating. A track pushes on a bead, so the bead follows its curve. These forces are necessary, yet they often do no work along the allowed direction of motion. They guide the system without directly driving it along its path. Lagrangian mechanics becomes powerful here because it can treat many constraints by describing only the allowed motion. If a bead is forced to remain on a hoop, we can describe where it is around the hoop. If a door is forced to rotate around a hinge, we can describe its angle. If a pendulum is held by a fixed string, we can describe its swing. The impossible motions are removed before the calculation begins. Instead of fighting the constraint at every instant, the method builds the constraint into the language of the system. This is the hidden simplicity of constrained motion. The system may be embedded in ordinary space, with many possible directions visible to the eye, while its true freedom is smaller. The pendulum bob exists in three-dimensional space, but a simple pendulum with a fixed pivot and fixed length has a much narrower freedom. It can swing through a restricted family of positions. By naming that freedom properly, the problem becomes cleaner. Some constraints are especially friendly to the Lagrangian method. They can be expressed as relationships among the coordinates of the system, such as a fixed length or a fixed surface. These constraints reduce the number of independent variables. Others are more subtle, such as the rolling motion of a wheel without slipping, where translation and rotation are tied together through motion. Even then, the Lagrangian framework often gives a systematic way to handle the restriction. It encourages us to ask what motion is truly available, instead of treating every visible direction as equally free. Once constraints reduce the problem to its real freedoms, symmetry can simplify it even further. Symmetry means that something about a system stays unchanged under a transformation. If a system behaves the same when shifted to another place, it has spatial symmetry. If it behaves the same after being rotated, it has rotational symmetry. If the rules governing it do not change from one moment to the next, it has time symmetry. This sounds simple, but it is one of the most important ideas in physics. A symmetry tells us that some difference in description does not correspond to a difference in physical law. If a perfectly smooth table looks the same at every point, a puck sliding on it does not encounter a special location where the laws suddenly change. If empty space has no preferred direction, a freely moving object does not find one direction more physically fundamental than another. If the laws of a closed system remain the same tomorrow as today, the system carries a kind of temporal uniformity. In Lagrangian mechanics, symmetry appears through the Lagrangian. If a change in a coordinate leaves the Lagrangian unchanged, that coordinate has a special status. It may describe a direction of freedom that does not affect the underlying balance of the system. Such a coordinate is often called cyclic, meaning that the Lagrangian does not depend directly on it. The motion may still involve that coordinate because its rate of change can matter, but the coordinate itself does not appear as a place where the system's energy structure changes. This is easier to feel through an example. Imagine a particle moving freely on a perfectly flat, featureless surface. There is no hill, valley, wall, or preferred location. Sliding the entire situation to the left or right changes the labels of position, but it does not change the physics. The surface has translational symmetry. Because the Lagrangian has no special dependence on where the particle is on that surface, a related quantity stays conserved. In ordinary language, the particle keeps its momentum unless something acts to change it. A rotating system gives another example. Imagine a smooth central force, such as ideal gravitational attraction toward a central body. The physics depends on distance from the center, not on the direction around it. Rotate the entire orbit, and the situation is physically the same. This rotational symmetry is tied to angular momentum. A planet sweeps through its orbit with a conserved rotational quantity because the central gravitational field has no preferred direction around the center. The full relationship between symmetry and conservation will become the focus of the next chapter. For now, what matters is the feeling of the idea. Symmetry removes unnecessary detail. If the system does not care about a coordinate, physics tells us to notice that indifference. The absence of dependence becomes information. What the system ignores can be as revealing as what it responds to. This is a beautiful reversal of ordinary thinking. We often look for what changes because change attracts attention. Physics also looks for what remains unchanged. Invariance is a clue. If something stays the same under a shift, rotation, or passage of time, the laws are telling us that a deeper structure is present. Lagrangian mechanics makes this structure visible because the Lagrangian is a compact expression of how the system is built. Constraints and symmetry work together in a quiet way. Constraints define the possible motions. Symmetry tells us which differences among those motions do not matter to the laws. A bead on a circular hoop is constrained to the hoop, and if the hoop is vertical in gravity, the top and bottom positions are physically different because height matters. If the hoop were horizontal and perfectly level, every angle around it might be equivalent. The same constraint can feel different depending on the symmetry of the environment. A pendulum is constrained by its string, but gravity breaks some of the symmetry. The downward direction is special. The pendulum has a lowest point because gravity selects a preferred direction. If the same pendulum were imagined in deep space far from significant gravity, the meaning of high and low would change. The constraint would remain, but the symmetry of the surrounding situation would be different. This shows that constraints and symmetries are not isolated decorations. They describe how the system and its environment fit together. The hidden simplicity of motion often appears when we stop asking every possible question and ask the right one. A rigid rod connecting two masses keeps them at a fixed distance, so their motions are linked. A wheel rolling without slipping ties the distance traveled to the amount of rotation. A particle in a central field does not care about absolute direction around the center. Each of these facts removes confusion. Each tells us that the system is simpler than a raw list of coordinates and forces might suggest. This is why Lagrangian mechanics became such a natural home for modern physics. It is sensitive to structure. It does not merely describe what moves. It describes what is allowed, what is equivalent, and what remains unchanged. These are the questions that lead from ordinary mechanics into deeper laws. Even in daily life, this way of thinking can make motion feel different. A bicycle rolling forward is constrained by its wheels and frame, yet its motion has a graceful order. A door opening is limited by its hinge, yet that limitation makes its motion simple and useful. A swing is restricted by its chains, yet the restriction creates the familiar rhythm. Constraints are not always obstacles. In physics, they often create the very shape that motion can take. Symmetry brings another kind of calm. It tells us that nature does not waste attention on meaningless distinctions. If a situation is truly unchanged by a shift, a rotation, or a translation in time, the laws respect that sameness. The world can be complex in appearance while carrying a deep economy underneath. So this chapter leaves us with a quieter view of mechanics. Motion is not just freedom. It is freedom shaped by restrictions and clarified by sameness. The path of a system becomes understandable when we know what it cannot do, what it can do, and what changes leave its laws untouched. In that combination, the complicated world begins to reveal a hidden simplicity. Let that thought settle gently. The day may have felt full of scattered movements, unfinished tasks, and restless directions. But beneath motion, physics finds patterns of allowed paths and quiet symmetries. Even complexity can have a calm structure, and tonight that structure can be enough to let the mind loosen, slow down, and rest. Chapter 8. Noether's Theorem: Why Symmetry Becomes Conservation. Noether's theorem is one of the most beautiful results in physics because it shows that every deep conservation law is connected to a hidden sameness in nature. To understand why this matters, begin with a familiar idea. Some things in physics remain steady even while everything else changes. A planet moves around a star, yet its total energy can remain constant in ideal isolation. A spinning skater pulls in her arms and spins faster, yet her angular momentum remains conserved if outside torques are negligible. A puck gliding across a smooth surface keeps moving with the same momentum if no external force interferes. These conserved quantities are signals that the laws of nature contain symmetry. Noether's theorem gives this connection its precise form. It says that when the action of a physical system has a continuous symmetry, there is a corresponding conserved quantity. The action is the path-based quantity used in Lagrangian mechanics. A symmetry means that we can make a certain smooth change in our description or in the system without changing the action. When that happens, something is conserved along the real motion. The word continuous is important. It means the transformation can be changed by tiny amounts. Shifting a system a little to the left, then a little more, then farther still, is continuous. Rotating a system by a tiny angle, then a larger angle, is continuous. Moving the entire description forward in time by a small amount is continuous. These smooth symmetries are the ones that lead to the conservation laws Noether's theorem describes. The theorem was developed by Noether, one of the great mathematicians of the modern era. Her insight gave physicists a new way to understand conservation. Before this, conservation laws were often known as useful facts. Energy, momentum, and angular momentum appeared again and again in mechanics. They were experimentally successful and mathematically powerful. Noether's work revealed why such quantities appear so naturally. They arise because the action does not change under certain transformations. Start with time. If the laws governing an isolated system are the same today as they were yesterday, the system has time translation symmetry. This does not mean the system itself looks the same at every moment. A pendulum may swing, a planet may move, and a spring may oscillate. The symmetry means that the rules are unchanged if the entire experiment begins at a different time. When the action has this kind of time symmetry, energy conservation follows. This gives energy conservation a deeper meaning. Energy is not merely a number that happens to remain constant in useful problems. It is linked to the uniformity of time. If the laws of the system do not explicitly depend on what time the clock reads, then energy has a conserved role. A swinging pendulum may exchange kinetic and potential energy, and a planet may trade speed for position in its orbit, yet the total energy remains fixed, because the underlying rules are the same from moment to moment. Now consider space. If a physical system behaves the same when shifted to a different location, it has spatial translation symmetry. Imagine performing the same ideal experiment in one empty region of space and then in another. If nothing about the laws changes because of the shift, this sameness is a symmetry. Noether's theorem connects that symmetry to conservation of linear momentum. Momentum is the quantity associated with motion in a direction. In Newtonian language, momentum remains constant when no external force acts. Noether's theorem reveals the deeper reason. Conservation of momentum reflects the sameness of space from place to place. If the action does not care about absolute position, then the system carries a conserved momentum. Space has no special location written into the law, so motion preserves a corresponding quantity. Rotation gives another example. If a system behaves the same after being turned around a point or axis, it has rotational symmetry. A central gravitational field in its ideal form depends on distance from the center. It does not prefer one direction around that center over another. Because of this rotational symmetry, angular momentum is conserved. A planet orbiting a star keeps a steady angular momentum when the gravitational influence is central and no outside torque acts. Angular momentum can feel less familiar than energy or ordinary momentum, but it appears everywhere. A spinning wheel, a rotating planet, a figure skater, and an orbiting moon all carry angular momentum. When outside torques are small or absent, this quantity remains conserved. Noether's theorem tells us that this conservation is the physical consequence of rotational symmetry. These examples show why the theorem is so powerful. It turns conservation laws into clues about the structure of reality. If energy is conserved, we look for time symmetry. If momentum is conserved, we look for spatial symmetry. If angular momentum is conserved, we look for rotational symmetry. The conserved quantity and the symmetry are paired. Each one gives meaning to the other. There's a subtle but important caution. Noether's theorem applies to symmetries of the action, not just to appearances. A shape may look symmetric to the eye, but physics asks whether the action remains unchanged under a transformation. The theorem belongs to the structure of the laws, not merely to visual beauty. A snowflake may have a visual symmetry, But the conservation laws of mechanics come from deeper continuous symmetries of the physical description. The theorem also requires care with open systems. In daily life, many objects exchange energy, momentum, and angular momentum with their surroundings. A rolling ball slows because friction transfers mechanical energy into heat and sound. A moving car changes momentum because the road, engine, brakes, and air are involved. Conservation has not failed in the broader physical sense. The quantity has moved into the environment. When we speak of conservation in a simple system, we usually mean that the system is isolated enough for the relevant exchange to be ignored. This is why ideal systems are useful. They let the symmetry stand out clearly. A frictionless surface, a perfectly central force, or a closed mechanical system may not exist perfectly in everyday life, but these models reveal the principles. Real systems can then be understood by asking how closely they preserve the symmetry and how strongly they interact with the outside world. Noether's theorem also shows why Lagrangian mechanics became so important in modern physics. The theorem is naturally expressed in the language of action in Lagrangians. When physicists build a theory, they often ask what symmetries the action should have. The answer restricts the possible forms of the theory and reveals the quantities that should be conserved. Symmetry becomes a guide for discovering laws rather than merely a decoration added afterward. In field theories, this idea becomes even more central. A field assigns physical quantities throughout space and time. Electromagnetic fields, matter fields, and other fields can be described through Lagrangian methods. Their symmetries lead to conservation laws, just as in mechanics. Some symmetries are familiar, such as space and time symmetries. Others are more abstract, involving transformations that do not look like ordinary movement through space. These abstract symmetries can lead to conserved quantities, such as electric charge. This may sound far from a swinging pendulum, but the logic is the same. A symmetry of the action gives rise to conservation. The difference is that modern theories use richer systems and more advanced forms of symmetry. The principle remains one of the great unifying ideas. From a simple particle to a field filling the universe, the relationship between symmetry and conservation continues to hold. There is something calming about this. Conservation laws are often taught as separate rules, as if nature keeps several different accounts in different ledgers. Noether's theorem shows that these accounts have a shared origin. Energy, momentum, and angular momentum are connected to the basic sameness of time, space, and direction. The universe preserves certain quantities because its laws contain certain invariances. This does not make physics simple in every detail. Many real systems are complex, and many symmetries are approximate rather than perfect. A crystal does not have the full smooth symmetry of empty space. A driven machine may change because energy is being supplied from outside. A system in a changing gravitational field may lack the time symmetry needed for simple energy conservation. Noether's theorem gives us a precise way to understand what changes when a symmetry is present, broken, approximate, or absent. A broken symmetry is especially interesting. If a system lacks a certain symmetry, the associated conservation law may no longer hold for the system by itself. If an external force chooses a direction, momentum in that direction may change. If a system is explicitly driven by a changing external influence, its energy may not be conserved internally. This is exactly what the theorem teaches us to expect. Conservation depends on symmetry, so when symmetry changes, conservation changes with it. This is why Noether's theorem is often described as one of the deepest results in theoretical physics. It connects what stays the same in the laws with what stays constant in motion. It lets physicists read conservation as a shadow cast by symmetry. It turns the silence of unchanged laws into a measurable quantity carried by a system. For this video, the essential idea can remain gentle. If nature's rules are the same through time, energy is conserved. If they are the same from place to place, momentum is conserved. If they are the same under rotation, angular momentum is conserved. Behind each conserved quantity is a symmetry of the action. Behind each symmetry is a kind of quiet sameness in the way the universe permits motion. Let this thought settle softly now. The world may appear full of motion, change, and uncertainty, yet some things remain held by deep invariance. Time passes, space opens, planets turn, and fields shift across the dark, but the laws carry hidden forms of balance. In that balance, motion becomes less restless. It becomes part of a quiet conservation, steady enough to guide the stars and gentle enough to rest the mind. Chapter 9. From classical mechanics to modern physics. Lagrangian mechanics began as a way to understand ordinary motion, but its real power became clear when physics moved beyond planets, pendulums, and falling objects into the deeper structure of space, time, fields, and particles. At first, it may seem surprising that a method developed for classical mechanics could matter so much in modern physics. Classical mechanics describes the world of familiar objects: stones, springs, wheels, machines, and planets. Modern physics deals with stranger territory. It includes high speeds, curved space-time, quantum uncertainty, electromagnetic fields, elementary particles, and interactions that cannot be pictured as simple pushes and pulls. Yet the Lagrangian approach survived this transition because it was never limited to one particular image of motion. It was a method for building laws from structure. In the simplest mechanical examples, the Lagrangian is often related to the difference between kinetic energy and potential energy. That is a useful doorway, but it is not the full meaning of the idea. In modern physics, the Lagrangian becomes a broader object. It is a compact description of what exists in a theory, how those things can change, how they interact, and which symmetries the laws must respect. Once this description is given, the equations of motion can be derived from the action principle. This shift is important. The Lagrangian is no longer only a tool for solving a pendulum. It becomes a way to write down an entire physical theory. If a physicist wants to describe a field spread through space, the Lagrangian can encode that field. If the theory contains particles, interactions, or constraints from relativity, the Lagrangian can be built to include them. The same logic that guided a bead on a wire can be enlarged until it guides the behavior of fields across the universe. One of the first great modern extensions came through relativity. Newtonian mechanics works extremely well for everyday speeds, but it is not the final description of motion when objects move close to the speed of light. In special relativity, space and time are connected more deeply than they appear in ordinary experience. Time can stretch, lengths can contract along the direction of motion, and energy and momentum must be described in a new way. The Lagrangian method adapts to this world because it does not depend on ordinary coordinates alone. A relativistic theory must respect the symmetry between different observers moving at constant velocities relative to one another. The action must be built so that all such observers agree on the physical content of the law. This requirement shapes the allowed form of the Lagrangian. The result is a description of motion that fits the geometry of space-time rather than the older picture of absolute space and universal time. This is one reason action became so important in relativity. The path of a freely moving particle can be described through the time measured along its own journey, called proper time. The particle follows a path through spacetime that has a special stationary property. The idea resembles the principle of stationary action in classical mechanics, but the geometry has changed. Motion is now a path in spacetime, and the rule must respect the structure of that spacetime. The same style of thinking reaches into general relativity, where gravity is no longer treated simply as a force pulling objects across space. Instead, gravity is understood as the curvature of spacetime itself. Matter and energy shape spacetime, and curved spacetime guides the motion of matter and light. This is a major change in physical picture, yet the action principle still plays a central role. The gravitational field can be described through an action built from the geometry of spacetime, and the equations governing gravity follow from requiring that action to be stationary. This shows how far the Lagrangian idea can travel. It began with mechanical systems moving under constraints, then became a framework for describing the shape and evolution of spacetime. The same deep pattern remains. Write an action that captures the structure of the system, then derive the laws from it. Another major transformation came through field theory. In everyday mechanics, we often describe individual objects with positions and velocities, but many physical realities are better described as fields. A field is something that has a value throughout space and time. Temperature in a room can be treated as a field. The surface height of water can be treated as a field. In fundamental physics, electromagnetic fields, matter fields, and other fields are central. The Lagrangian approach is naturally suited to fields. Instead of describing a few coordinates changing in time, it describes quantities defined at every point in space and time. The Lagrangian is adapted into a form that applies locally throughout space-time, and the action gathers its contribution across the region being studied. From that action, field equations can be derived. Electromagnetism is a powerful example. Electric and magnetic phenomena were once studied as separate effects. Later, they were unified into a single field theory. The electromagnetic field can be described with a Lagrangian that respects the symmetries of space, time, and charge. From this structure come the equations governing electric and magnetic fields, light, radio waves, and much of modern technology. The Lagrangian does not merely calculate a trajectory. It expresses how a field behaves. Quantum physics changed the picture again. In classical mechanics, a system follows one definite path when the initial conditions are known. In quantum theory, the behavior of matter and light cannot be reduced to a single ordinary path in the same way. Outcomes are described through probabilities, and microscopic systems show wave-like and particle-like behavior depending on how they are measured. Even here, action remains deeply important. In one formulation of quantum theory, a particle's behavior can be understood by considering many possible paths. Each path contributes to the final result in a way determined by the action. For ordinary large-scale motion, paths near stationary action reinforce one another most strongly, while many other contributions cancel out. This helps explain why classical mechanics emerges from quantum behavior, when objects are large enough and actions are large compared with the quantum scale. This connection is profound. The principle of stationary action is not simply discarded when quantum theory appears. Instead, it becomes part of a larger structure. Classical motion appears as the calm, large-scale pattern that rises out of many quantum possibilities. The old path is still there, but it is now understood as a special limit of a deeper theory. In quantum field theory, the Lagrangian becomes even more central. Particles are treated as excitations of fields. Electrons, photons, and other particles are linked to underlying fields that fill space-time. Interactions are described through terms in the Lagrangian that show how these fields influence one another. The structure must respect relativity and quantum principles at the same time. This is the language behind the standard model of particle physics. The theory describes known elementary particles and several fundamental interactions using fields, symmetries, and a Lagrangian framework. Its construction is guided by symmetry principles, including gauge symmetries. A gauge symmetry is a freedom in the mathematical description that leaves observable physics unchanged. Although this idea is abstract, it has real consequences. It helps determine the kinds of interactions particles can have and explains why certain quantities are conserved. Here, the Lagrangian becomes almost like the grammar of a physical theory. The fields are the basic words. The symmetries are the rules of meaning. The interaction terms describe how the words can be combined. From the full structure, physicists derive predictions about particles, forces, scattering, decay, and the behavior of matter at very small scales. This does not mean modern physics is easy because it uses Lagrangians. The mathematics can become highly advanced. Some theories are difficult to solve exactly. Some require approximation, experiment, and careful interpretation. Yet the Lagrangian approach gives the laws a disciplined form. It tells physicists how to begin, how to preserve symmetry, and how to derive motion or field behavior from a single organized principle. It also creates a bridge between areas that might otherwise feel separate. Classical mechanics, relativity, field theory, and quantum physics all use different concepts, yet the action principle appears across them. A planet, a light ray, a gravitational field, and a quantum particle do not behave in the same way. But the idea of constructing an action and finding the resulting laws keeps returning. This recurrence is one reason physicists trust the framework so deeply. There is something quietly astonishing about that. A method that helps explain a swinging pendulum also helps shape the theories used to describe the smallest known particles and the largest structures of spacetime. The details change dramatically, but the style of explanation remains. Nature is described through quantities that respect symmetry, encode interaction, and generate motion through stationary action. So Lagrangian mechanics is not merely an alternative to Newton's laws. It is a doorway from classical motion into modern physical thought. It teaches us to look for the structure behind equations, the symmetry behind conservation, and the action behind motion. It shows that physics often advances by finding a language broad enough to survive when our picture of reality changes. As this chapter settles, imagine the path from a pendulum to a field, from a planet to space-time, from a moving object to the deep patterns of the quantum world. The universe becomes vast again, but also strangely connected. Its laws may change form from one scale to another, yet a quiet thread remains, carrying the idea of action through the whole fabric of physics. Chapter 10. Why the universe may be written in action. There is a reason the idea of action feels like a final doorway in mechanics. It gathers motion, energy, time, symmetry, and law into one quiet principle. After traveling through Lagrangian mechanics, we can now look back and see why the subject feels different from an ordinary method of calculation. It does more than help solve problems. It changes the shape of the question. Instead of asking only what force acts on an object at one instant, it asks how the full motion of a system fits into a deeper pattern. That pattern is expressed through action. Action is a physical quantity built from the Lagrangian over time. The exact mathematical definition belongs on paper, but the meaning can be approached in words. The Lagrangian describes the balance between motion and configuration for a system. As the system follows a possible path, that description is accumulated through time. The accumulated quantity is the action. The real motion is the one for which the action has a stationary property when compared with nearby possible motions. This statement is precise, yet it can feel strange. We are used to laws that sound immediate. A force changes motion. A field pushes or pulls. A collision transfers momentum. The action principle speaks in a different tone. It treats a path as a whole. It says the motion that actually happens is distinguished among nearby possible motions by a special balance. The system does not think, choose, or search. The principle is a mathematical way of expressing the law. Still, it gives motion an unexpected elegance. The word action may suggest activity, but in physics, it is more subtle. It combines energy and time. This matters because motion is never only about where something is. Motion unfolds. It has duration. A planet does not simply occupy a point in space. It traces a history. A pendulum does not simply pass through an angle. It swings through a rhythm. A field does not merely have a value at one place. It changes across space-time. Action is suited to this kind of description because it belongs to a history rather than to a single instant. This is why action can feel like a natural language for the universe. It does not depend on a single preferred viewpoint. The same physical motion can be described with different coordinates, and the action principle still keeps its meaning when the theory is written properly. This is important because nature is not tied to the labels we use. A coordinate system is a human tool. A physical law must express something that remains true beneath the tool. This point becomes especially clear in relativity. Space and time are not separate stages in the old absolute sense. They form a connected structure, and different observers may divide that structure into space and time in different ways. A law written through action can be shaped to respect that deeper structure. The action becomes a compact way to express the rule in a form that does not depend on one observer's private perspective. Action is also closely tied to symmetry. When the action remains unchanged under a smooth transformation, a conserved quantity appears. This is one of the great reasons action is so central. It does not simply produce equations of motion. It reveals what the laws preserve. The sameness of time is tied to energy. The sameness of space is tied to momentum. The sameness of direction is tied to angular momentum. The action is where these relationships become organized. In this sense, action is a meeting place. It gathers motion and conservation, change and invariance, freedom and constraint. A single expression can contain information about what moves, how it interacts, what is allowed, and what remains unchanged. That is a remarkable compression. Physics often advances by finding such compression. a way to write many facts as one principle. There is another reason action feels fundamental. It works across scales. In ordinary mechanics, action gives the path of a falling object, a swing, a spring, or an orbit. In field theory, action describes how fields evolve through space and time. In general relativity, action can be used to derive the equations that describe the curvature of space-time. In quantum theory, action helps determine how possible histories contribute to physical behavior. Each domain changes the details, but the idea keeps returning. This return should be treated with care. It does not prove that the universe is literally made of action, as if action were a substance hidden behind matter. It does not mean nature consciously minimizes anything. It means that our best physical theories often become most elegant, general, and powerful when written in terms of action. The phrase, "written in action," is therefore a way of describing the form of the laws, not a claim that action is a material ingredient. Still, the form matters. In physics, a good form is not just decoration. The way a law is written can reveal what it truly says. Newton's laws made force and acceleration clear. The energy viewpoint made transformations and conservation clear. The Lagrangian and action viewpoint makes structure clear. It shows which descriptions are equivalent, which symmetries matter, and which motions are physically possible. This is why action principles often feel less cluttered than force descriptions. A force description may require us to identify every push, pull, tension, and support. An action description often begins with the whole structure of the system. What is its Lagrangian? What symmetries should it respect? What variables describe its real freedom? From there, the equations follow. The method is not magic. It is disciplined bookkeeping at a deeper level. A simple example can make this calm. Imagine a stone thrown gently through the air. Newtonian mechanics can describe the stone through gravity acting downward. The action principle gives the same path through a different view. Among nearby possible paths connecting the same endpoints in the same time, the real path has stationary action. The stone does not know the path ahead. The statement is simply another exact way to describe the motion. Yet the second view hints at a wider unity, because the same idea can later describe light, fields, and space-time. In quantum physics, this wider unity becomes even more fascinating. At microscopic scales, nature does not behave as though every particle always follows one sharply defined classical path. The quantum description involves probabilities and amplitudes. In one powerful formulation, many possible histories contribute. The action associated with each history affects how it contributes. When the action is large compared with the quantum scale set by Planck's constant, the contributions away from the stationary path tend to cancel, and the classical path emerges. This gives the old principle a new meaning inside a deeper theory. This connection is one of the reasons the action viewpoint feels like more than a historical curiosity. It survives even when the picture of reality changes. The old image of a tiny object traveling along one path becomes insufficient at small scales, yet action remains part of the language that connects quantum behavior with classical experience. The familiar world appears as a calm pattern rising from a more delicate underlying structure. The same kind of endurance appears in modern field theories. Instead of beginning with particles as tiny billiard balls, physicists often begin with fields and symmetries. A Lagrangian is written to describe those fields and their interactions. The action built from it gives the laws. This approach has helped organize some of the most successful theories ever developed. It gives physics a way to build from principles rather than from guesswork alone. Of course, there are still deep questions. We do not yet have a complete, universally accepted quantum theory of gravity. We do not know whether the action principles used today are final or whether they are shadows of something deeper. In some areas, the correct action is known only approximately, or the equations are too difficult to solve exactly. Scientific humility is important here. The action viewpoint is powerful, but power does not make it the last word. Yet even with that caution, the idea is extraordinary. The universe may not be written in action in a literal poetic sense, but action may be one of the closest languages we have for writing the laws of motion, fields, and space-time in their most unified form. It lets physics speak about whole histories, not just isolated instants. It links motion to symmetry. It allows different observers and coordinate systems to express the same physical reality. It reaches from classical mechanics into the deepest theories we have built. At the end of this journey, Lagrangian mechanics becomes more than a chapter in classical physics. It becomes a change in how we imagine law itself. The universe is not seen merely as a collection of objects being pushed through space. It becomes a web of possible motions, constrained by structure, shaped by symmetry, and expressed through action. Every falling stone, every orbit, every wave, and every field can be understood as part of that larger pattern. And now, as the final idea settles, there is no need to hold it tightly. Let action remain as a quiet image. Motion gathered across time, balanced among possibilities, written in the deep grammar of nature. The day can loosen into that thought. The body can rest, the mind can soften, and the universe can continue its silent motion, carrying its laws through the dark with calm and patient precision. And now, my friend, we have reached the end of this quiet journey through Lagrangian mechanics. We began with ordinary motion, followed it into energy, action, symmetry, conservation, and finally into the deeper language that connects classical mechanics with modern physics. So let the ideas settle softly now. There is no need to hold every detail at once. It is enough to know that beneath the movement of the world, physics has found a calm and elegant structure. If you're still awake, you can continue the journey with another video and drift a little deeper into the hidden patterns of the universe. And if sleep is already close, then let the night take over gently. Sweet dreams among the stars.